So let's start with the meditation. Just lift your tongue slightly, a couple of centimeters. Feel the chi, taste the chi around the edge of the tongue. And then feel with your breath, chi in your breath. Breathe deep into the well of chi beneath the breath. Enjoy feeling fulfilled. Feel the presence in your breath. In this episode, I'm going to show you why I believe quantum mechanics is a con. Science is evidence-based, and as Richard Feynman says, if your theories don't fit the facts, it's the theories that are wrong, not the facts. And what's happened in quantum mechanics is that when evidence appeared that disproved the uncertainty principle of Werner Heisenberg, instead of recognizing the evidence, physicists have discounted the evidence, they've ignored the evidence. And in science, that is anathema. Because once you put the theory first and bury the evidence that disputes the theory, then you no longer have science. The whole of integrity of science is lost. And this has been going on since 1935 in the world of physics. I mean, there's something seriously wrong with quantum theory, quantum mechanics, that it's unintelligible. You know, in the 19th century, the beauty of the physics was that people could understand it, and there was a great interest in science. But science is losing its interest because there's so much that people can't understand in the fundamental physics. You know, as Richard Feynman said of quantum mechanics, we never understand it, we just get used to it. You see, what happened in the history of science was that when the vortex atom theory was unable to explain the way atoms absorb and emit light, the spectral lines, they dropped the physics. They dropped the vortex atom theory. And when Niels Bohr, the Danish scientist, managed to explain spectral lines by applying quantum theory to the atom, then his theory took precedence and he took the world of physics by storm. And the center, the epicenter of theoretical physics, moved from Cambridge in England to Copenhagen in Denmark. And what happened is that he assembled a team of young scientists, young theoreticians, the best minds he could recruit, to develop the quantum theory in Copenhagen. And there was a young man called Werner Heisenberg who was the star of the team. And he needed a bright idea, a good idea, to justify his role in the team so that he could take the initiative. And he was out walking, pondering on the quantum leap that Niels Bohr had proposed. to explain spectral lines. And it was nighttime, and he saw a man walking under the lamplights. And when the man was under a lamp, under one of these gas lamps, he appeared. But as he walked away from that lamp to the next lamp, in the dark area that wasn't illuminated between the lamps, he disappeared. And then he reappeared again under the next lamp. So Heisenberg proposed that it's only when things interact with light that we can be certain of their existence. The Copenhagen interpretation of quantum mechanics is that things only exist when they're observed. It's all based on that initial experience he had. And he took that idea that you can only be certain of the existence of the man when he's under the lamps. You don't know whether he's existing, you see, you can't be certain. He took that whole concept of uncertainty and developed it further to propose the observer effect, that the act of observing quantum particles will so influence them that you become uncertain. For example, you bounce light off things to observe them. And when you bounce light off subatomic particles, because you need very energetic light to look into the smaller realms, like you need an electron microscope rather than a light microscope to look at into the smaller world, in the smallest things. The hard light hitting a subatomic particle will give it a kick, and you'll no longer be certain about where it is. So the act of observation displaces it. So he put forward this principle that the more certain you are of the position of a particle, the less certain you are of its velocity, and vice versa. And he formulated this as a formula in 1927. Albert Einstein was deeply unhappy about this. He argued through the night with Werner Heisenberg, reducing the younger man to tears. And he described the uncertainty principle as a rule which is calculus, so ingenious in its complexity as to be impossible to prove wrong. But a few years later, evidence appeared in physics that actually refuted the uncertainty principle. And this occurred in 1935 at Cambridge, when James Chadwick discovered the neutron. Let me explain. A neutron is formed when an electron falls into a proton in a process called K-capture. The mass of a neutron is the mass of an electron and a proton. And a neutron is unstable, and when it falls apart outside of the nucleus of the atom, an electron and a proton appear. It's called beta decay. So that suggests a neutron is an electron bound to a proton where the opposite charges are cancelled out by the coexistence of opposites. So that's really simple. So why don't physics accept it? Well, it's simple, this. If a neutron is an electron bound to a proton, you know where that electron is with certainty from the diameter of the proton. You know it's in there somewhere. And that certainty of the position of the electron when applied to the Heisenberg formula suggests such a high degree of uncertainty and velocity that some neutrons will have electrons with no velocity and other neutrons will have electrons with the velocity 99.97% of the velocity of light. And at those high velocities, the electrons are more massive than the electrons at rest. An electron with a velocity of 99.97% of the velocity of light will have a mass 40 times the mass of an electron at rest. So you should expect neutrons to have a range of masses between the mass of a proton and 1 electron and the mass of a proton and 40 electrons. And they don't. They all have exactly the same mass, which is the mass of an electron and a proton, and slightly more. It's just slightly more than an electron and a proton. And that's accounted for because the kinetic energy of the electron can't just cease to exist when the electron is locked into the proton. So it gets tangled up. You know, I've got that capture theory. So that kinetic energy is transformed into mass, which accounts for the extra mass. But it's unstable. That energy, that kinetic energy that's locked into the proton is not stable, and it causes the electron to bounce. And I believe that in the nucleus of the atom, electrons are escaping from protons, they're escaping from neutrons, but they get snapped up by another proton. So there's a constant exchange of electrons between the protons in the nucleus. It's something that could be tested, actually. And I use a cat and mouse analogy. The electron's like a mouse, the proton's like a cat. So the neutron is a cat with a mouse in its jaws. And when the mouse escapes, it gets grabbed by another cat when you've got a group of cats. But when you've got a very big atomic nucleus, it's radioactive, it's unstable, because what's happening is that some of the mice are escaping from the group. And that's beta decay. That's where the electrons escape from the nucleus altogether. But you see, Professor Wu, a Chinese-American physicist who was an expert on neutrons, when she lined atomic nuclei that are radioactive in a magnetic field, she noticed that all the beta decay electrons were coming off directionally, which suggested they were coming off a particular site on a neutron and decayed into a proton. And also, these neutrons have a magnetic moment. That is, it's a magnetic moment of 1.91 nuclear magnetrons, and it can't have that value of magnetism if it's not a charged particle, because it has to have charge in order to have magnetism. But the most conclusive evidence that the neutron is a bound state of two particles came when, in 1957, when three experimentalists, Smith, Purcell, and Ramsey, actually measured a weak electric dipole over the neutron. That is, on one side, it's just slightly negative in charge, and on the other side, slightly positive. But the value is so weak it's been discounted by the world of physics. They're looking for excuses, you see, to discount evidence. They don't want this bound state model. Instead, what they've decided is that the proton is formed of 3 quarks, 2 up quarks and 1 down quark. And when it gets hit with an electron, when the electron comes in, you don't get a bound state of the 2. The electron, due to the action of a weak nuclear force, the electron disappears and a new totally chargeless particle comes to replace the electron and the proton, because an up quark's turned into a down quark. I mean, this just sounds like something out of alchemy. It sounds like a bit of a fable to me. Desperate attempt. In my physics, in my book, The Superenergy and the Quantum Vortex, I disprove quark theory along with the general theory of relativity, Big Bang theory, and quantum mechanics. So I don't believe in quarks. They don't exist. So going back to this electric dipole moment, this weak electric charge, it reminds me of the mad professor of puddings, who put out a theory that when you bake plums into a pudding, you don't get plum pudding, you get a Black Forest Gateau, because due to the action of a weak cooking force, the plums change to cherries. So you have Black Forest Gateau, not plum pudding. So the electrons are represented by plums, the protons by the pudding. The weak nuclear force is the weak cooking force. And the Black Forest Gateau is the completely different thing. You see what I mean? Up quarks turn to down quarks, plums are turned to cherries. But one day in his lab, this represents, a little bit of the story represents the Smith, Purcell and Ramsey experiment measuring the weak electric dipole of the neutron. One day in his lab, a student baked plums in a pudding, and when he got his plum pudding out, he licked it and he tasted a plum. And he went up to the professor. He said, "Hey, professor, that's not a Black Forest Gateau. I tasted it. No cherries there at all. There's a plum in there." So, you know, this measure of the weak dipole is like licking the neutron. It's just very, very weak. Just a little taste, you see. That's discounted by the professor. Too weak. That's not a genuine measure. Got to do a scientific measure, not a lick. And he got really angry. He said, "Have you learned nothing that I've taught you about plums turning to cherries, up quarks turning to down quarks?" And how could the student argue? This was none other than the president of the Royal Society of Puddings. So you can see there's a lot at stake here. Karl Popper said, if you have a theory that all swans are white, another white swan doesn't make your theory any truer, but a single black swan will disprove your theory altogether. And where I'm sitting recording this video, I'm in Devon, near Dawlish. Dawlish is my local town. And the emblem of Dawlish is the black swan. So every time I go to town, I'm reminded of the black swan story of Karl Popper. And the neutron is the black swan to quantum mechanics, disproves quantum mechanics, like spectral lines disprove the vortex atom theory. So you see, if I can disprove quantum mechanics, I don't have to go along with their whole thing about naive realism. I can use a model from the 19th century physics. I can resurrect it and bring it back. So it's back to the vortex model and apply it at a subatomic level with great success. And we now need it if quantum mechanics is a con, because I say it's a con because evidence has been disregarded. in order to protect it since 1935. Since 1935, it's been a downright con. So we can bring back the vortex theory at a subatomic level. And as for quantum physics, quantum mechanics, the great world of physics, I mean, everything they believe in, I mean, will be shattered because they put so much into quantum mechanics. It's been so successful. It's the most successfully tested theory in the history of science. So if it goes, credibility of science itself, the scientific criteria for truth, comes into question. Science as we know it will be shattered. What will all the skeptics do if their precious science is wiped out? This is the way science advances, actually, from shock to shock. And the truth will out. Eventually, the truth about the neutron will out. Look, the neutron is the particle that they use to detonate weapons of mass destruction. And it would be divine retribution if the neutron turned out to be the nemesis of quantum mechanics, of quantum physics, of science as we know it. So I leave you with that thought.